Okay, so for chapter 9, what we're doing is just what we did last 2 days, and this stuff, which is a review. Functions and their inverses. So we're going to find inverses again. We did this in chapter 7 when we were working with logarithms. We worked with inverses. We found that they are just a reflection across the line, y equals x. So all we're going to be doing is reflections again and working on the inverses, switching x and y's and solving for y. One thing to recall is that the vertical line test can help you determine whether a relation is a function, right? We draw a vertical line. If it ever intersects more than one point, it would not be a function. Well, there's another test called the horizontal line test. And the horizontal line test tells me that if I intersect a graph more than twice with a horizontal line, then the inverse is not a function. Okay? So vertical line test tells you whether a relation is a function or not. Horizontal line test tells you whether the inverse is a function or not. So we have two examples here, the red line and the blue one. Start with the blue one. I think that's letter A. Is that graph, is the inverse of that graph a function or not? In other words, does it pass the horizontal line test? I know that it's not a function itself, but is the inverse a function? So if I take a horizontal line, and anywhere I move this on the blue line, does it ever intersect more than one point? And the answer is no. So the inverse is a function. For the red one, use my same horizontal line, and in this area, all these areas here, it intersects more than one point, so the inverse there is not a function. So the horizontal line test just tells you whether the inverse is a function or not. Vertical line test told you whether a relation is a function. Right. Horizontal line test tells you whether the inverse is or not. So is this one a function or not, the inverse? Okay. All right, yes it is. Any vertical, horizontal line here is never going to intersect more than one point at a time, so the inverse of that would be a function. Okay. All right. Finding the inverses again. All right, we talked about working your way through them by working backwards or undoing things, okay? But we also talked about switching x and y and solving for y. So let's look at that. So here I have the function cube root of x plus 1. They want us to find the inverse and then determine whether it is a function and state its domain and range. So first of all, let's graph the function. First, we're going to graph it to make sure the inverse is a function. So here's what the graph looks like. All right, let me change that for a second. Okay, so here's the graph of this function. All right. Starts here. Actually, that's not the whole thing. Right? What does it look like on your calculator? Anybody graph it on your calculator? Because this actually continues on. Oops, and looks like this. Okay. But first of all, is the inverse of this a function? Right. Will this pass the horizontal line test? Okay, and the answer is yes, it will. Okay, so the inverse is going to be a function. So we've got to find it. So we're going to switch x and y and solve for y. So what's the first thing I do to solve for y? Okay, we got to get it by itself. So what do I do first to get by itself? Okay, I need to get rid of the radical for 1, right? And I need to get rid of that plus 1. Which one do I do first? Get rid of the radical or subtract 1? All right, so how do I get rid of that cube root? Okay, I have to cube it. Raise both sides to the third power. So we get x cubed equals y plus 1. So y equals x cubed minus 1. Now, we said it's a function, right? Okay. Since we said it's a function, then we have to use inverse notation. If it was not a function, then we would just continue to say y equals. But since it's a function, we have to use inverse notation. All right, then they want us to find the domain and range. You can't recognize that. You're kidding me. Okay, so the inverse is going to look like this. Maybe. There we go. Okay. So what's the domain and range for x cubed minus 1? Okay. All right. Does it ever stop moving left and right? Okay. There's no radical. Right. There's no x in the denominator, and there's no logarithm. Okay. As long as we don't have those three things, then the domain is all real numbers. And since it's going from negative infinity to positive infinity, then the range is all real numbers. So here's the inverse. It is a function. The domain is all real numbers, and the range is all real numbers. So to find the inverse, all you need to do is switch x and y, solve for y. And you can talk your way through it too, okay? If I had the cube root of y plus 1, and I put a number in for y, what's the first thing I would do? We would add 1, right, first, okay? And then we would take the cube root of that, okay? So to undo that, then we would cube it, and then we would subtract 1. So the way we talked our way through it before, you can do that, continue to do that same process. One-to-one functions. One-to-one functions are, here's the easiest way to look at them graphically to think if they are. If they're always increasing or always decreasing, they're one-to-one. These two here are one-to-one because this graph is always increasing as it goes from left to right. This one is always increasing as we go from left to right. So as long as they're always increasing or always decreasing as you go from left to right, then they are one-to-one. We can use composition of functions to verify that two functions are inverses. Okay? So inverses, if they're always increasing, always decreasing, then they are one-to-one. So we want to find out whether we have functions are one-to-one, whether they're inverses of each other. So it says if the composition of two functions equals the input value, which is x, then the functions are inverses. So to tell whether two functions are inverses, what we're going to do is calculate f of g of x and g of f of x. So we're going to plug them in for each other, and if they equal x, then they are inverses. If they don't, then they're not. If you prove that one of them is true, then you have to show that the other one is true also. Right? But if you show that one of them is not true, then you don't have to do the other one. So as soon as you prove it's false, but if it's not false, then you need to show it both ways, that it actually is a true statement. So we want to determine by composition whether each pair of functions here are inverses. So we have f of x equals 3x minus 1, g of x equals 1/3 x plus 1. So we're going to do composition. We're going to do f of g of x. And if they are inverses, when I'm done, it will equal x. That's if they are inverses. When I'm done, it's going to equal x. So f of g of x, I'm going to replace this x here with an f of x with 1/3 x plus 1. So 3 times 1/3 is x. 3 times 1 is 3 and minus 1. So this equals x plus 2, which is not equal to x. So they are not inverses. So you're just using composition. We're looking to see if they equal x. If they do, then they're inverses. If they're not, then they're not going to be inverses. If it doesn't equal x, then they're not inverses. All right, so let's look at the graph for a moment of them. Here's the graph of y equals 3x minus 1. I thought I had the other one there. I guess not. Okay. So here's the graph of nope, not that one. Now, if those are inverses, then they're reflections over the line in y equals x, right? Which means that they will intersect at or intersect on the line y equals x. So notice where they intersect. Come on. You're not going to do this for me? I guess not. I guess it'll only do two graphs. So if I draw in the line y equals x, do they intersect on that line? Okay, the answer is no. So since they don't intersect on that line, then they're not inverses either. Okay, so but we proved it here by showing that when I simplified f of g of x, it did not equal x. So I don't have to do g of f of x. But if it did equal x, then you would have to do g of f of x to prove that it works the other way also. You can't just do it the one way. You got to show it both ways. All right, so let's look at another one. All right, let's look at letter, we'll do letter B here. We'll do it together. Use the radical. So f of g of x, square root of x minus 5 squared plus 5. Okay, we put this whole thing in here for x. Now, the thing is, even if you did this wrong, okay, all right, it's not going to come out to be correct. But the thing is that if I multiply this out, we get x all right. If I foiled this, all right, it equals this. All right, square root of x times square root of x is x. Negative 5 times the square root of x. Negative 5 square roots of x, and it doubles. Okay, so that'll give us negative 10. Square negative 5, get positive 25. Is this going to simplify to be equal to x? Doesn't look like it, does it? All right, there's no way. So for letter B, those are not functions either. Or they're not inverses, excuse me. They're functions, they're just not inverses. But like I said, if one works, then you have to check the other way. You can't just do it once. All right? If it works, you got to do both.